In this question, it has given that there is a silicon device with one side is heavily doped and other side is lightly doped by pentavalent atoms. So it is given as N plus N silicon device, and the given concentrations are also given on both sides with its intrinsic concentration, and we are going to calculate the magnitude of built-in potential barrier. What is the value of V naught that we are going to calculate for this device, N plus N silicon device? So we will get the concept of this one using a p-n junction. You can do it in two methods. So first method, later we'll go for the second one, and we'll start from p-n junction. From that one you are going to find this. As you know, p-n junction is made up of, for an intrinsic semiconductor, first you are going with intrinsic semiconductor, which is also called as pure semiconductor. If one half is doped with trivalent impurities, that means this side it becomes p type, and other half, if it is doped with pentavalent impurities, it becomes n type. Before doping, if you only consider the intrinsic semiconductor, every semiconductor will have holes and electrons. All the electrons or holes are going to be at the same energy levels. But whenever it is doped with, one half is with trivalent, other half is with pentavalent, then the electrons and holes in p type will not be at the same energy level of electrons and holes of n side. So if there must be a current to flow, then the electrons from one side to other side it has to move, as well as from other side to this side. So at that time they have to either get energy to excite, otherwise they have to lose the energy to move from one side to other side. In forward bias, it requires external energy to move from one side to other side, that is climbing. In reverse bias, they will dissipate energy as they are moving from one side to other side. So that means there must be a difference between energy levels on both sides. Since both are different now, P and N, so that there is an energy level difference, that is called as potential barrier energy. That difference is indicated as E naught, potential barrier energy. And units of this one is electron volts. V naught is potential barrier voltage. It is given as E naught by Q. This is called as potential barrier voltage, and units are going to be volts itself. So we know the equation for V naught. V naught is equal to Vt, thermal voltage, multiplied by natural logarithm of Na Nd divided by Ni square. Otherwise you can use this equation Vt natural logarithm of Pp naught divided by Pn naught. Otherwise Vt natural logarithm of Nn naught divided by Np naught. These three equations, depending on the availability of the data, you can use either of these three equations. Look at this one, when to use this equation. If you are looking at this one, if you know hole concentration on p side, that is Na, acceptor concentration, and electron concentration on n side, that means donor concentration Nd, and if you know intrinsic carrier concentration, it requires three parameters: hole concentration, electron concentration, and intrinsic carrier concentration. And if you are coming for the second equation, if you know hole concentration on p side and hole concentration on n side, then you can use this equation where it requires only two parameters. Pp naught means Okay, hole concentration in P side under open circuit under equilibrium condition. Pn naught, hole concentration on N side under equilibrium. So if you know hole concentration on both sides, you can calculate. Otherwise, if you know electron concentration on both sides, that means electron concentration on N side as well as P side. So Nn naught, electron concentration on N side under equilibrium, electron concentration on P side under equilibrium. If you know, you can calculate V naught. This also require only two parameters. Okay, so we can conclude that whenever there is a difference in the material, there must be a difference in energy levels for the electrons residing in one side and electrons residing in other side. Not only for electrons, for holes also. So there must be some energy barrier is going to be created. That energy barrier can be calculated using these three equations. Now come to the actual question. Here given is intrinsic semiconductor, one side is heavily doped, that means left side is heavily doped, so that it becomes N plus, and right side is lightly doped, so it is N type. Okay, initially it is intrinsic semiconductor only, but one half is heavily doped, the other half is lightly doped, so that it is N plus N, and the concentration as 10 power 18 and 10 power 15. Donor concentration on N plus, donor concentration on N minus. It has given that ND1 and it is ND2. Okay. Now again there are difference in energy levels because one is heavily doped, the other is lightly doped. The electrons are more excited on one side, electrons are less excited on one side. So there will be energy level differences between them. Again there will be a potential barrier energy is going to be required, and that you can write it as Q times of V naught. V naught can be calculated using either of these three equations. Okay, but remember that one, this is portion 1, this is portion 2. If you know in both cases, in both regions, if you know electron concentration, you can calculate, or you can calculate if you know hole concentration on both sides. Otherwise, if you know hole concentration on region 1, electron concentration on region 2, as well as intrinsic carrier concentration, then you can use this equation to calculate V naught. But it has given only electron concentration on one side, electron concentration on other side. That means you are going to calculate V naught using this equation. Vt natural logarithm of Nn naught, Nn naught divided by Np naught. Nn naught means electron concentration on N side, Np naught means electron concentration on P side. So this will be treated as majority carriers and this will be treated as minority carriers. So here you can write majority carriers means more number of electrons, minority carriers means less number of electrons. So you are going to write Nd1 divided by Nd2. Nn naught will be equal to this one, because which side is heavily doped, Np naught will become which side is lightly doped compared to. So Nn naught is Nd1, Np naught is Nd2. Vt thermal voltage or volt equivalent of temperature, which is given as kT by Q, that is 25 millivolts. From this one, this is 25 millivolts multiplied by natural logarithm of 10 power 18 divided by 10 power 15. 25 millivolts into natural logarithm of 1000. It is equal to 1.26 volts. So the right answer for this question is D. D is the right answer for this question. Okay, this is first part. So from using first part you can calculate, that is method 1. Now we will see how to calculate the second part. Now we will see second method. The second method is using energy band diagram. So if you draw the energy band diagram for the n plus n device, okay, this is potential barrier and both are n type. So this is EC conduction band, and this is EFI intrinsic Fermi level, and it is EV valence energy level. EC is generally called as lowest energy level of conduction band. EV is generally called as highest energy level of valence band. Okay, and we know that whenever a semiconductor is doped, okay, if it is pentavalently doped, as the doping is going to becoming higher and higher, the Fermi level related to that n-type semiconductor moves towards conduction band, and it may touch conduction band or it may go deep into conduction band depending on the doping density. Now n plus side is heavily doped compared to n side, so this will be more towards EC. So this you can write it as EFN plus, and it is lesser. This is EFN. Whatever the difference you are going to get, that is called as E naught. E naught is the height of potential barrier. Height of potential barrier. This is the amount of energy it requires to move a charge carrier from one side to other side. If you are not able to supply this much energy as externally, so no movement is going to be taking place, current doesn't takes place in the semiconductor. So in forward bias you must apply minimum of this much voltage. This much voltage, that means V naught is going to be treated as cut-in voltage, so it is E naught by Q. If you apply this much cut-in voltage, then conduction takes place. We are going to calculate E naught is equal to EFN plus minus EFN. How to calculate this one? So the difference between EC and the difference between EC minus EFN plus can be written as KT natural logarithm of NC by ND1. This is equation 1. Okay, and next similarly the difference between EC and EFN. EC minus EFN, actual meaning of EC minus EFN means the position of Fermi level of n-type semiconductor with respect to conduction band. That is relative position of Fermi level on n side with respect to conduction band. In this one, EC minus EFN plus means relative position of Fermi level on n plus side with respect to conduction band. This can be written as KT natural logarithm of NC divided by ND2. This is second equation, and we require EFN plus minus EFN, that is E naught. So subtract 1 from 2. So what you are doing is nothing but 2 minus 1. Then EC get cancels and EFN plus 1 will become plus. So you are going to get E naught is equal to EFN plus minus EFN from these two, and the E naught can be written KT natural logarithm of NC by ND1 minus KT natural logarithm of NC divided by ND2, and we know logarithmic rules, so you can write it as KT natural logarithm of NC divided by ND1 multiplied by ND2 divided by NC. Sorry, this is ND2, it is ND1. So this will be ND2 and it will become ND1. So finally what you are going to get is KT natural logarithm of ND1 divided by ND2. This is E0, and what we require is V0. V0 is equal to E0 by Q, that means KT by Q, which is given as 25 millivolts into natural logarithm of ND1 is 10 power 18 divided by 10 power 15. So it is 25 millivolts into natural logarithm of 1000, that is equal to around 0.726 millivolts. So the right option for this one is D again. You can do it using either second method or first method. So in both cases the right answer is D itself, definitely. Thank you.